All right. So we got a free response question here that I wrote to combine basically every conservation law that we've looked at some point. So to do this, I've created the classic ballistic pendulum design. So we have a mass m at a velocity v. The projectile comes in, it strikes the crate, it deforms a little bit, it sticks. So this first case is sticky clay projectiles. And then it rises just to some max height, delta h. And first, we're asked about the velocity of the crate after the collision. So, uh, show the velocity of the system directly after the collision is 1/10 of the original incoming velocity. So we just have two objects colliding, no external forces because we just have a massless string here. So it's just going to be conservation of linear momentum. So we know that momentum is conserved in this process because there's no external force. Again, it's not conserved the entire time, just during the collision, because after the collision, gravity is going to change the momentum, but during the collision, momentum is constant. So before the collision, we just have a mass m moving at a velocity v, and then after the collision, we have a composite mass of 9m for the crate and the sticky projectile together, moving at some final velocity. So mv is equal to 10 times mv final. The mass cancels, so we get v equals 10 times final velocity, or the final velocity is just 1/10 of the initial, which is what we're trying to show. Derive an expression for the maximum vertical displacement of the crate. So don't overcomplicate this. So after the collision takes place, we can conserve energy because then it's only gravity that's going to be acting on our system. That's going to be the unbalanced force external to the system. But again, we count that as a potential energy, so it's totally fine just to say that kinetic energy at the bottom, right when it starts swinging, is equal to gravitational potential energy at the top. So the only pitfall here is trying to take kinetic energy before the collision and setting it equal. Because again, when these things stick together, this sticking together takes energy to happen. So we can only conserve energy after the collision takes place. But then we just have 1/2 times 10m times Vf squared is equal to 10m g delta h. And again, we're just calling the bottom point 0 so we can make our math a bit cleaner. So we see that the 10m's cancel as per usual. So we get delta H is just going to be Vf squared divided by 2g. But we actually found Vf in the previous part and even told us that Vf is just going to be V over 10. So we get V squared over 200g as our maximum vertical displacement. And we didn't even need theta. All right. And also, I guess another acceptable answer would be L minus L cosine theta is delta H. So there's actually another acceptable answer if we just looked at the figure. That's the same thing. Because again, if we have a length L here, that means that the vertical is going to be L cos theta. Suppose that instead of using sticky clay, bouncy rubber projectiles were used instead. How will the maximum height of the pendulum change using these new projectiles? Okay, so we should think about this once again with a momentum approach. So we know that before the collision, the sum of the momentum of the system is to the right. Because again, we're just sending a projectile at the pendulum to the right. And we should note that this is equal in both cases. So in the sticky case, all we have is a giant crate with the projectile stuck to it, and it's just got to get a little bit of momentum or velocity in that direction in order to get the momentum to be the same. So we just get all our momentum to the right from that one object. But in the bouncy case, we actually get one of our projectiles to bounce to the left. So that actually introduces negative momentum into our system, which means that in order to compensate, because momentum has to be conserved, that must mean that the crate has more momentum in the second crate. And since the crate actually has less mass than it did in the sticky case trial, well, to get more momentum with less mass, your V has to go up. So thus, it's going to go higher. So justify our choice conceptually. So again, I will just kind of write it out here. So in both cases, the initial momentum is to the right. Then we'll make this text box wide enough for us to actually get some good writing in here. In both cases, the initial momentum is to the right. And equal. In the bouncy case, there is leftward momentum introduced after the collision. And as such, the crate needs more rightward momentum in order for conservation of momentum to hold, since the crate has less mass, it needs more velocity to generate the required momentum, and thus goes higher. Okay, so quite a lot of words going on here, but that is a complete response to this. So again, it's all about the fact that this case, you're getting negative momentum, so the crate actually has more sort of work to do in order to balance out, to get the momentum to be constant. And it goes higher because it's initial KE. Since its KE is larger. Derive an expression for the velocity of the crate directly after the collision under this new setup. Well, this is going to be way easier than the thing we just did, because we can just say that, of course, the sum of momentum before equals the sum of the momenta after. Before, we just have an m at a velocity v, and it's just v, not vo. And after, we have projectile mass m at a speed of negative v over 2, don't forget that, plus a mass of 9m at some velocity v2 that we don't know. The mass cancels from all the terms, so we're just going to get v equals negative 1/2 v plus 9 v2. So we get 3/2 v is equal to 9 v2, or v2 is equal to 3/18, which is 1/6 of v. And notice that is higher than 1/10. And 1/10 was our v after the collision in the first case. And lastly, here's our rotation. So suppose that now it's revealed that the pendulum string actually had significant mass. And instead of being a string, it should be a rod of mass 3m and length L. So same total mass of our system, it just turns out we need to put some in the rod. So suppose that suppose that the original clay projectile travels at the same speed and sticks to the block once again. Which of the following of the bullet pendulum Earth system are conserved during this collision? Or sorry, just bullet pendulum system. You can select more than one quantity. So, first, let's first eliminate kinetic energy. It's definitely not kinetic energy. Because it sticks together. Any inelastic collision, by definition, takes a lot of kinetic energy out. So, it's not KE. Now we have to look at the different momentum types. So, the issue here with linear momentum is that there is a force coming from this hinge. So, we don't know exactly what it is, but there's probably some force acting in some direction, causing this whole system to move. And it's at this contact point. Again, that didn't exist before because we had a massless string. But now we actually can't ignore that. So there is an external force. So linear momentum is no. And kinetic energy is no. But angular momentum is yes. Because even though we do have an unbalanced force, it's at the hinge location. So its lever arm is 0, so it can't generate a torque. So let's generate each torque. Or sorry, let's go through each choice. Let's get our handy text box. So linear momentum is not conserved due to an unbalanced force at the pivot point. Angular momentum is conserved since this force acts at the pivot, generating no torque. And then kinetic energy is not conserved because this is an inelastic collision. Which results in maximum KE lost. You could also do an argument where sort of some of the kinetic energy must have gone into actually deforming the clay, which is why this is a result we have access to. And then lastly, solve for the linear velocity of the crate directly after the collision, and we're given the moment of inertia. So we want the linear velocity of the crate. Well, we're just going to conserve angular momentum, because that's the only thing we can conserve, so it has to be this. It has to be the angular momentum to start equals the angular momentum after. So to start, we just have angular momentum from the point particle. So there's nothing rotating at the start. So as such, we can just write our first definition of angular momentum, which is just going to be m times v times L for our point mass, because everything's perpendicular. Since the velocity is perpendicular to r, since we have this, we have that r cross v is going to be exactly, there's no angle to deal with. So that's what it looks like after. And then after the collision, it's going to rotate. So we have rotational angular momentum. So we have I of the system times omega. So to find the angular momentum of the system, we're just going to combine it. So we have I of the rod plus I of the crate at a velocity of omega. Moment of inertia of a rod is 1/3 ml squared, so it's 1/3. The rod's mass is 3m. And the crate, it's just, all of the crate is a distance L away, and the thing attached to it. So we have 7m, a distance of L away. So it's 7 ml squared, because a point mass is ml squared times omega. All right, now we can do some simplifying and get mvl is equal to ml squared plus 7 ml squared all times omega. So mvl is equal to 8 ml squared omega. Mass cancels. One of the L's cancels. So we get V equals 8 omega L. And notice that omega times L is just going to be the velocity at the bottom, because we have V is equal to omega R. So, or you could just replace omega with V over L and get the same result. So we get V at the bottom is just 1/8 of the original. And that's that. So again, I like this problem because it allows us to use all our different conservation laws in different contexts. So to start, we had to use conservation of linear momentum because it was just a collision. But after that collision ends, we're able to use conservation of energy because there's no more energy loss. Then we looked at some conceptual aspects using momentum conservation. But then we went down to actually the angular case, where now that we have a moment of inertia, this typically is a case where P is not conserved because you have some sort of unbalanced force coming from a pivot point, which is right here in this problem. So we had to solve using every different conservation law at some point.